You have turned off your microphone.
Yeah, thank you. All right, greetings, everybody. It's 1 o'clock, and we're at lecture three of our class on cosmology. And today we're going to talk about expansion of the universe in more detail than we have in the first two lectures. We certainly mentioned, in fact, emphasized that one of the key findings very recently is the expansion of the universe and the fact that the expansion is accelerating. This is a discovery that dates back to the very late 1990s and has an interesting history um, related to the Hubble Space Telescope. In 1990, the Hubble Space Telescope was launched, and the first images that were obtained were uh, bad, really so bad that real good science could not be conducted, far from the expected performance. And it took the better part of a year to figure out why. Um, the the reason you probably have heard about is that the 10-foot, 2.4 meter primary telescope has the wrong curvature. It's an exquisitely good mirror. We'll talk about this more when we in lecture five, where we go into a lot of detail about the telescope technologies that have really opened our eyes to the dynamics of the universe. But the Hubble mirror is an excellent mirror, except it's the wrong shape by just a little bit, a tiny fraction of the width of a human hair. And it took, as I say, approximately a year to figure out the problem and then figure out what to do about it. And eventually, because the Hubble is serviceable, at least it was back then, because the space shuttle could approach and dock with the Hubble spacecraft, uh, and optical correction was installed, built by. Oh, I'm losing my voice again. Hang on, I'm going to mute. Built by. Oh my gosh. Thanks for being patient. I'm going to struggle through this. The people at Ball Arrow. Jeez, holy mackerel. Maybe it's working now. I don't know. The people at Ball Aerospace in Boulder built the corrective optics, and they were installed in a structure about the size of a an old phone booth. You all remember phone booths, and that corrected the set of instruments that were permanently installed in Hubble, as well as the instruments that could be replaced. In subsequent astronaut missions, the replaceable instruments had their own correction to accommodate the defect in the telescope mirror. And so, through a series of visits to the spacecraft, the optics were corrected. And then by the mid 1990s, so the correction was made in the first corrected images appeared in 1993. And by, say, 1997, 1998, the scientific results were in the hands of the people who were interested in the expansion of the universe. And their expectation was that by doing careful measurement, replacing what had been done by Edwin Hubble back in the 1920s and 30s, that we would see that the universe had an initial expansion rate first detected by Hubble, and that there was likely to be a slowing of that rate, that is a deceleration, still expanding, but slowing in its expansion rate. And that's not what the data showed. Two different groups had access to the data from the improved Hubble Space Telescope, and both independently found that the universe is not, the expansion rate is not getting smaller, it's getting bigger. And this was shocking. So let's get into the multiple features of this, but it's all because 25 years ago, we had actually had a working big space telescope that could do much better than anything on the ground. And yes, we are recording. Oh yeah, and I forgot to mention, Rich has just in the last few minutes asked, did he see that the rate of expansion may be slowing a bit? Yes, that's been reported. There's a set of survey telescopes. These happen to be on the ground. And their data is suggesting that the expansion rate is slowing. This has been in the news since back in September, August. And I wasn't intending to talk about it because this is the kind of thing that needs time to make sure that a wide variety of researchers look at the data and get a chance to digest it. But by the time we get done with this class, you will have the tools, that is the vocabulary and the understanding of the concepts, to really understand what appears in the media. The problem is, and we're going to talk about this later today, is a lot of what is reported incorrectly. So we have to be cautious about this. But yeah, there is a hint that the expansion rate is slowing. All right. So last week, we looked at the concordance map that we have. So we had back in 2010, a collection of data from different sources, including leftover influence from the acoustics of the early universe. That's this green stripe. We had data from the cosmic microwave background measurements. And by the way, this orange stripe did not include, let me think about this. No, it did not include the very best microwave background data we got from the European Planck spacecraft. We had from the model of the universe that would pertain if the universe has a flat geometry, which is another result from the microwave background. And we had a lot of supernova data derived from, by 2010, we had lots of supernova data that helps define the distance to the various galaxies that are the markers for the expansion of the universe. We put this all together in 2010, and it all points to this little area right here, a sort of balance point for the amount of dark energy and the amount of matter in the universe. And then I showed you last week also, let's get rid of that. Well, last week I also showed you that improvements moved the center, this orange ellipse, now repeated here, moved the center to the center of this blue ellipse. This is using additional data from the lensing that is created by the presence of dark matter coming from distant objects being influenced by dark matter, and that the trajectory of that light is altered. So that includes this new data. And we're now pointing right here. This is pretty up to date now. Point that the amount of dark energy in the universe 0.69, and that the amount of total amount of matter at 0.31, of which about a fifth of that is atomic matter and the rest is dark matter. So this is where we are now, and people are constantly playing with this and making little adjustments. But and here's the description of what goes on in the lensing events. A distant galaxy with a supermassive black hole generating a stupendous amount of energy finds its way on the way to the telescopes we have, which are very close to Earth. But along the way, it encounters massive objects, namely galaxies or clusters of galaxies. A cluster has maybe between 1,000 and 10,000 galaxies all bound together gravitationally. And that distorts the space-time in the region of that cluster. And so these trajectories are altered, and we can tell that they're altered because we can see multiple, I call them mirages. We see multiple examples of the light from this single galaxy, and that can be used to help us focus on the spot here that shows us the energy distribution in the universe, dark energy versus matter. Here's a drawing you've seen many times. We're going to skip over this, but it's the one that dates back for probably 20 years and illustrates the main features of the evolution of the universe from the Big Bang, whose origin is still unknown, and then to the Dark Age when there were no stars, and then the formation of stars and galaxies. And we're going to repeat this multiple times because it's a changing landscape due to new data coming from the James Webb Space Telescope. So let's look at some alternate ways to try to digest the idea that the universe is expanding. So we have analogies. The problem with these analogies is when you draw them, they have an edge. And as we've discussed multiple times, the universe does not have an edge. If it did, we would be embedded in an even larger space. The idea that the whole universe is in something the shape of a beer can doesn't work. We know from the geometry that we detect from various sources of scientific information. But that beer can has to be inside of something. And instead, a better analogy comes up on the next page. But this does help us understand the expansion that we are experiencing. If we take a loaf of bread, not a loaf, a dough of raisin bread, for example, and put it in a baking tin, the raisins are a certain distance apart on the average, and then we bake it. In the process, that dough expands and we get raisin bread, and the same raisins are there, but they're farther apart. Furthermore, every raisin in the dough appears to be at the center of the expansion. All these, if we had little sensors on all these raisins, we would see all the objects that are detectable are moving away from every object. So this is a way to think about what's going on in an expanding universe. That the key points are, if you conclude that the universe is expanding, it means it was smaller in the past. Indeed, this is the contribution from the Belgian priest, Lemaitre, who said if it's bigger now than it was in the past, it must have been even smaller prior to that past. And if we go all the way back, we would find a primeval atom, is what he called it. We now call that the Big Bang. So the key features of the expansion, that all the objects in the universe are moving away from each other, is conveyed by this thought experiment with bread dough and raisins and so forth. Again, please keep in mind this analogy fails because it shows an edge, and the geometry we know about does not include that. I'll show you next. Here's a more desirable analogy where we have a small universe. In this case, let's imagine that the universe is two-dimensional. That is, all these little galaxies that I've put on here are stuck on the surface of a sphere, and that sphere is getting bigger. And as it gets bigger, the galaxies move apart from one another. All the observers on these galaxies see everything else going away from them. Notice that in the drawing, I've taken care that the galaxies do not get bigger. This is because the stars in a galaxy are bound to the galaxy they're embedded in by gravitational forces that far exceed the expansion that's going on in the universe. We'll get into that in more detail. But this is an example of a shape for the universe that could exist, except it's lacking another dimension. We know we live in a three-dimensional space, and so we have to bend our brain to imagine that our three-dimensional space appears on a higher dimensional surface, possibly a sphere, that can accommodate a three-dimensional surface. And the way we can think of this is a sphere, like the ones I've illustrated here, they're called a two-sphere. The reason is that it only takes two dimensions to define your location. And here on Earth, we use the words latitude and longitude for that. Now imagine that there's a thing called a three-sphere. And a three-sphere would have the same geometric structure, but would have three dimensions. And a question remains whether our universe appears flat. And remember, we've measured the geometry of the universe through the cosmic microwave background. I showed you last time that it shows us the universe is flat. We can't distinguish a purely geometrically flat surface from a surface that's so large and is curved. But if the curvature is big enough, if the radius of your sphere is big enough, you can't detect the curvature. If you go out and look at the street in front of your house, it takes some very sophisticated instruments to detect that right where you live, there's a curvature to Earth. In fact, lots of other factors get in the way, the geology of your neighborhood and so forth. But even in ideally laid out, it takes some long distance measurements to detect the curvature, and we'll talk about those in a second. So the nearby objects are, and another key factor in the expansion of the universe using this analogy is that the more distant objects, for example, if we use this as the Milky Way, the more distant object, like this one, recedes faster in an expansion than a nearby galaxy. And I have a little cartoon to illustrate that for you. Now, let's, just for fun, let's replace these galaxies with ants. And the ants have the ability to walk on this surface. They don't know about up or down, but they can go forward, backward, left, and right. And let's say that they're equipped with noise. They can send signals. As their universe expands, confined to this surface, the time it takes for a chirp from an ant here to get to an ant here will increase you can see it on these drawings. What's more, while the sound produced by this ant is traveling to this ant, the universe is not static in this model. The universe is getting bigger. So the sound waves that are making their way from here to here get stretched during their travel. And so the sound wave received by this ant have now changed in pitch. This is akin to the Doppler shift that we all hear if you're standing on the sidewalk and an ambulance goes by. You hear high pitch as it's approaching and a lower pitch after it passes you because the source is moving away from you. So not only are the objects moving away, any signal we send between these objects gets stretched, and we'll see how this influences what we know about the expanding universe we live in. Now, it's also possible, depending on the rate of expansion of this ant universe, this two-dimensional universe, that the expansion rate is big enough that the signal sent by this ant never gets to this one, because as that sound signal is traveling to the neighbor, the universe is getting bigger, and if the expansion rate is big enough, this distant neighbor will never get the signal. That's why I said in the first lecture that when we talk about our universe, we talk about our observable universe, because there's a limit to how far out a signal can have been sent in the past and still get to us, because our universe is getting bigger. What's more, our universe is accelerating in its expansion rate. And that has implications for the volume of space in which ancient galaxies could have sent signals that we will eventually get. And that's why we conclude that there's a vast universe beyond our reach that we will never hear from. And that all comes from the expansion rate, which in our case appears to be getting bigger. So here's another, this sentence covers this idea of the redshift that we've talked about so many times. In the case of the ants, a sound wave that gets to the neighbor coming from this, heading to this neighbor, that sound wave gets stretched. Eventually, the frequency that this receiver may get from its long-distant neighbor gets stretched so much that it becomes undetectable, because the pitch changes to a lower and lower pitch as that universe expands. And eventually, the time it takes to detect the signal will be longer than the lifetime of the universe. So that's when these signals just disappear. They're undetectable, even in theory. And when that happens, we say that this ant that sent a signal in the long distant past has now gone over the horizon of the ant that was hoping to receive a signal. And we see this here on Earth. I'll show you an example in a second. So here are the ants. And there's more detail on here. But here are those ants I was talking about. And they just get farther apart as the universe expands. And this is detail you can read at your leisure to see if it comports with your the way you think about the space around you. And here's where I mentioned a 3-sphere, which is a possible shape for our universe. So here I'm re-emphasizing the idea that there's no edge to the universe. These objects just get farther and farther apart. And that leads us to talk about the origin. What was the volume of the universe when the Big Bang occurred? And it's very important to not get confused and think that the bang is like a firecracker that you might set off on the 4th of July, that the firecracker is the expansion of the universe. And that's not the case. It's that the universe itself was tiny. So as I say here in this sentence, the Big Bang was not a bomb that went off in the center of a pre-existing void. That doesn't apply. We just have an expanding universe, and we have to get comfortable with the concept that the universe we live in is a three-dimensional spatial universe that in the past was very tiny. And the way the professionals describe this and try to avoid getting confused and coming to wrong conclusions is it just means the galaxies that existed in the early universe, indeed everything that existed in the early universe, was much closer together than it is now. And not worry about, then we can have a conversation about what the universe is doing without worrying about the shape. Let's see, I just saw a chat question. Okay, well, we'll deal with this. So we have an administrative issue about the link to the lecture notes. Maybe at the break, we can get people to comment whether they were able to get to the lecture notes. Okay, so this recapitulates the things I've been saying for the last 20 minutes. Well, our theory now is the expansion rate of the universe is propelled by dark energy. The more energy you put into a volume, the more that volume wants to expand. It's kind of like forcing gas, a gas like air into your automobile tire. If you had an inner tube, like in the old days, that tube would want to expand. You're putting energy in and it creates pressure. And the pressure insists, if there's nothing in the way, that insists on expansion of the universe. The bizarre thing about dark energy is that it appears in a volume of space regardless of how that volume was created, dark energy jumps in there and fills that volume. And that leads to more pressure to expand the universe, and it's a runaway effect. Initially, in the early universe, gravitational forces restricted the influence of dark energy, but now the universe is, and has been for a long time, big enough that the volume of dark energy that is spontaneously appearing as the universe expands, that has now overtaken the gravitational effect and is pushing the galaxies apart. So here's where we talk about the more distant objects leaving your neighborhood faster than the nearby objects. So if we have a universe where the galaxies are spaced like this, where I have these 6 lines representing 6 galaxies, and later in the future, the 6 galaxies have run away from each other by the same amount. So the distance, this is the early universe, and they're 1 unit apart. Sometime later, they're 3 units apart. But that means that number 6 has receded from number 1 at a higher rate, indicated by the slope of this line, than number 2 has receded from number 1. And that's, in fact, what we see. And now let's talk about numerically, what is the expansion rate? It's about 25 kilometers per second. That's a velocity. That's sort of like, kind of like 15 miles per second for every million light years we are from an object. So if we look at a galaxy a million light years away, which is pretty close. Remember, the size of our Milky Way galaxy is a few 100,000 light years. So a galaxy a million light years away is receding from us at 25 kilometers per second. But this applies to more distant objects too. So if you, instead of looking at an object a million light years away, suppose we look at an object a billion light years away, which is 1,000 times farther, then the velocity of that distant object is 1,000 times bigger. Now, in the astronomical parlance, we don't use million light years. We use something called parsecs. A parsec is just over 3 light years. And so this number becomes this number. And if you look at the numbers in a scientifically literate article in media, you'll see a number close to 70. So the number that the professionals use is the expansion rate is about 70 kilometers per second, about 3 times that, per megaparsec. A parsec being about 3 light years. So 72 kilometers per second for an object about 3 million light years away. So this is not that fast. It's like 4 times the speed of a satellite that orbits Earth, 72 kilometers a second. Much faster than you drive on the highway, but tiny compared to the speed of light. But that's for an object a million parsecs or a million light years away. For more distant objects, the velocity relative to us is much, much higher. And I'll show you examples of this in a later chart. What we find is that the most distant object we can see is the surface from which we get the cosmic microwave background. It's about 45 billion light years away from us. And that means that its speed relative to us, which is a sort of a fictitious thing because we can never measure this, but the relative speed of the surface of the microwave background is about 3 times the speed of light. We'll see something more specific about that in a minute. So there's more text here to try to help you if you want to spend some time reading this, to try to convey this idea that we're in an expanding universe with a boundary beyond which we cannot get signals. And here's the closest thing I can offer you. A ship at sea in the center of this circle on the Indian Ocean can see another ship. Let's say you're in the captain's, in the cabin where they steer the ship. You're some distance above the ocean surface. And out far from you, you can see a distant ship, depending on how tall it is, but there is a boundary there beyond which you can't even see a really tall ship. For example, if you're here in this location I chose, you can't see Mount Everest. It's up here and it's huge, but because of the curvature of this spherical surface, this spherical space that ships and mountains sit on, even though the Mount Everest is huge, you can't see it from here because you'd be looking through part of the straight line from your eye to the top of Mount Everest. You'd have to look through the rocks and ocean of Earth. So take a few minutes, read this. Perhaps that helps again. So having said all these factual things, what's the history of the discovery of the expansion of the universe? And to understand the context, we have to go back to the early 20th century. And in the early 20th century, the first inklings that there was a problem with measuring the lifetime of the sun was beginning to get interrogated because the science of quantum mechanics started in the early 1900s, and there was hope that they could explain how is it that the sun produces the heat output that it does, because the original concept was that the sun was producing heat and light used by a chemical process. But people knew that could not be right. They could see the size of the sun, you can measure how much material is in the sun, and just, let's say the sun was made of a pile of carbon in the form of wood or coal, and you set fire to it and raise the temperature enough to get the measured value for the sun's output here on Earth, the sun would have burned out in a few million years. This is before the concept of nuclear energy had been discovered. That didn't happen until the 1920s and 30s. But people knew that this problem had to be solved, because if the stars in the sky were all producing energy based on chemical reactions, the universe would be filled with burnt out piles of ash. So that didn't comport with the idea that the universe was older than that, because respectable values for the age of Earth coming from geologists suggested that Earth was billions of years old. So there was a problem. And as quantum mechanics matured, finally coming into a form we use today in the late 1920s, the idea of nuclear fusion as a method of energy production in stars became understood. And then a reassessment of this issue of where the energy comes from and what is the age of a universe that contains stars like the sun, that became more understood. It wasn't until the late 1930s that Hans Bethe, Nobel Prize winner, was able to explain how our sun produces energy by fusing hydrogen into helium and a small amount of other heavier elements. Bigger stars can produce elements that our sun cannot. Our sun is limited to producing by fusion to elements up to the atomic number and the atomic mass of iron, but not beyond that. Furthermore, prior to Edwin Hubble's work that revealed the expanding universe, the assumption was that the universe was a static, eternal volume in which we happen to evolve and learn how to build telescopes and do science. And the idea of a static universe persisted up until just after Einstein produced his grand idea, his theory of gravity. So Einstein's theory of gravity was first in a mature form in 1917. And to deal with the prevailing idea that the universe was a static volume, remember, this is before Hubble's work, to explain a static universe that didn't collapse on itself because of gravitational forces, Einstein thought up an idea and tinkered with his equations, and he put in something he called a cosmological constant that was energy in the space between the galaxies that kept the galaxies from noticing each other gravitationally and collapsing the universe. Otherwise, there could not be a static universe. You had to somehow balance what was seen and what was assumed. But as soon as his theory came out, 1917, Alexander Friedman, who I introduced, I think, in the first lecture, and Lemaitre, the Belgian priest, realized that his equations could be used to determine the expansion or contraction rate of the universe if we just knew how much matter and other forms of energy were in our universe. And we'll go through that. So here's Einstein, and he had a tremendous impact on not only this issue of the structure of the universe, but also on quantum mechanics. And I think the next Ali session, I will be talking about the history and structure of quantum mechanics. So you might want to watch for that if you want to see how this strange thing called quantum mechanics works. Here's Lemaitre and Alexander Friedmann. So what they found, what Friedmann and Lemaitre found, was depending on the content of the universe in terms of matter and light and other material unknown to Friedmann and Lemaitre in the early 1920s, that we could have one of these possible futures, not a static universe, but if there was enough matter, their equation derived from, and it's normally called Friedmann's equation, his equation showed that if there was enough matter in the universe could be expanding. Let's say here's our present distribution of galaxies, starting from a primeval atom, that the universe could continue to expand, but eventually the matter density in the universe through the influence of gravity would cause the universe to decelerate and cause what we call the big crunch. And this is what the astronomers and cosmologists of the late 1990s expected to find once they got the Hubble telescope working and making precise measurements of the expansion rate at the current time. That's not what they found. They found this, that the primeval atom led to the universe we now experience, but that the something undefined was adding energy persistently to the universe and causing its expansion rate to increase. There are also these two unlikely but possible kinds of universes that come from Friedmann's equation. One where the universe has an early expansion rate and just slowing down, and the slower it goes, the slower the slowing goes, and it just keeps creeping along, slowing and slowing. And another one was that the universe just continues to expand at a constant rate. So here's another way to look at this. We could have what the Friedmann equation showed us, that we could have this so-called closed universe, that's this one, where the universe was expanding to the point where it is now. This is shows the relative size of the universe. But then there'd be a big crunch here. Another possibility are these two coasting kind of things, flat or open. And this is the one we see. And it implies that there should be some place on that concordance map. We didn't know when, we didn't know where in the late 1990s, but somewhere on there had to be a combination of the total matter, there's an M hidden there, and some other form of energy that was propelling this increasing expansion. Now, how did the astronomers find the increasing expansion? They looked at the velocity of distant objects. And with the Hubble Space Telescope and subsequent developments, they can measure the velocities of distant objects more and more precisely. And as I explained in lecture 1, the challenge is not measuring the speed, the challenge is measuring the distance. It's very hard to measure the distance to these objects. But progress, lots and lots of progress has been made, and we're going to cover that here in a second. So the question is, what's propelling this expansion? And instead of using the term cosmological constant, which is what Einstein used to try to keep the universe from collapsing, we now call this dark energy. And there are other terms you'll see, but those are the ones we'll use in in this class. Oh, here they are listed. No, somewhere in this set of lecture notes. There's a list of the terms that are used. So we don't do math in this class, but we can look at equations like you look at a piece of art and see what are the components of the expansion. So this is Friedman's equation. And let me move something out of my way you can't see. Each of these terms contributes to the energy in the universe. And this equation deals with each of these terms. So one issue is, what is the radiation density? And here we're using a term radiation, not in the normal everyday parlance of X-rays. If you go to the dentist and they do an X-ray of your teeth, there's some radiation, some X radiation involved in looking at your teeth. Here we're using radiation in the terms of light, any form of light, including the light we can see, infrared, ultraviolet, X-rays, and so forth, light we can't see. But if you put it all together, it depends the way it influences this parameter here, we now call the Hubble constant. This amount of light distributed in the volume of the universe is a factor, but notice a volume normally has a cube to it. So an engine, automobile engine, is frequently characterized by cubic inches. But this doesn't have cubes. It has a fourth power here. And the reason is, in an expanding universe, the influence of radiation comes from how much light there is in the universe, but also the light gets stretched because of the expanding universe, and that reduces the influence over time of the light that's in the universe. That's the redshift that we've mentioned so many times. So radiation enters the equation as, with this size of the universe, to the fourth power. The amount of matter, the amount of atoms in the universe, and now we include in this the dark matter that was discovered very recently. That total amount of matter, whether it's atomic or some other thing, gets spread out in the volume of the universe. And here we do see the volume cubed. Turns out that the curvature, it takes energy to curve space and space-time, that comes in the form of a square. And dark energy doesn't care about the size of the universe. As I said, as the universe expands, any vacuum that's created in that process is immediately filled by dark energy. That's our model for the universe now. And our model works very well. So this equation is a way to write Friedman's equation. And this is the current expansion rate of the universe. Okay. So I've already said this. Friedman, Lemaitre, I've already pointed out that Lemaitre was the one who said, if the universe is getting bigger now, it must have been smaller in the past, and in the far, far past, it was a primeval atom, unexplained. Meanwhile, Edwin Hubble was exploring with his telescope, he was exploring the galaxies around our galaxy, and to everyone's surprise, he realized that the distant galaxies were receding from us faster than the nearby galaxies. So this all happened in the course of sort of 10 years. Our view of the universe changed dramatically. Now, to solve the equation that Friedman came up with is a mathematical challenge, but we can simplify it because we now know that the amount of radiation in the universe, all the light that's ever been produced by stars and the cosmic microwave background, if you put all that together and put it into a universe as big as ours, remember the distance from us to the surface produced the cosmic microwave background is 45 billion light years. If you raise that number to the fourth power, it's a stupendously large number. So we can ignore this contribution to Friedmann's equation. And we also know that the curvature is essentially zero, so we can throw that out. And we're left with two things that determine how the universe is expanding, and that is the amount of matter and the amount of dark energy. And if you treat each of these separately, you get some sense of what's going on. For example, if your universe has just light in it, you get a growth rate of only has mass. The universe expands according to this. That's time raised to the 2/3 power. The universe will expand, but the expansion rate eventually settles down to a constant value. If you have a universe filled with light, it follows this sort of orange curve. But if you have a universe that only has dark energy in it, it follows the green curve, and it accelerates to higher and higher expansion rates all the time. Here's Hubble checking on equipment in his telescope. Now, because, I'm going to repeat myself, because it's so hard to measure distance to distant galaxies, Hubble's pioneering efforts were conceptually correct, but numerically incorrect, because his distance estimates were just way off. He can measure the velocity of those distant galaxies, but not their distance. And by the way, there's one galaxy that's coming toward us. It doesn't have a red shift, it has a blue shift, and that's Andromeda, our nearby neighbor, which in a few million, 4 billion years will intersect with the Milky Way galaxy, and the two of them will, who knows what will happen. So here's another view of one of the telescopes he used. Now, let's point out that in Hubble's lifetime, he died in the 1950s. He did not realize that the galaxies he was looking at were moving away from us because of expansion of the space between the galaxies. He thought they had an inherent velocity relative to us, and that we were all embedded in the same space. So we can grant him a pardon on this, because he was a pioneer, and pioneers frequently get things wrong. But in principle, the reason we see the redshift is that the space between galaxies is getting bigger. And that comes directly from Friedmann's equation, if you put the right numbers in. And I've talked about this in the past. If you're standing on the shore and a boat goes by, you could assume that the boat is moving through the water at a certain velocity that you measure. But you have to take into account the possibility that the water in which the boat is floating, that water is moving relative to you. And there can be a combined effect. What we now know is the galaxies we look at that have these very large velocities away from us are in their local space. They're not moving at all. And if we could go there, we could do measurements of their relative velocity in the space in which they're embedded. But the key factor here is the expansion of the space between the galaxies. And here's our examples of redshifts. Here's if we measure the spectra of a particular element. Let's say this might be hydrogen, or could be hydrogen. If we measure it in a laboratory, here's our wavelength scale. This is all visible light out to roughly there. The human eye can see out to this far in the red, and we would see these lines. A nearby galaxy, one that's receding from us, might have a tiny little redshift, and you could see this arrow connecting this spectral line to that spectral line, that's not straight up and down. So it got a little tilt because that galaxy is moving away from us at a low velocity. A more distant galaxy has a higher relative velocity, and this line is this line coming from a distant galaxy because of the much higher velocity that it has than a nearby velocity, the nearby galaxy. And the most distant galaxies we see are heavily redshifted. This is why the James Webb Space Telescope was designed to concentrate on the red spectrum, not limited to this red, but way, way out, way off the screen. That's what James Webb looks at, because it's looking at spectral lines that we recognize shifted by huge numbers. And we'll talk about how big those shifts are. So, in addition, we get the rotation rates of the galaxies, because if you look at a galaxy, this edge, if it's almost certainly rotating, and this part of it might be approaching us and have a blue shift, and this part is receding from us and have a red shift. And by knowing those numbers, we get the rotation velocity. This is one of the many ways we have detected the presence of dark matter in the universe, because we can measure the velocity of stars on each side of a galaxy, and we discover that galaxy is behaving in a way that the luminous matter, the atomic matter that I've sketched here, is not the only matter in this galaxy. There has to be something else there, and we now know, or we now call that unknown stuff dark matter. There are many other ways to detect dark matter. So here's an example of Hubble's data. This is right out of one of his papers in the late 1920s, where he's estimating the distance in millions of parsecs. Remember, a parsec is around 3 light years. And he's measuring, so he's trying to get data on the distance, and he's measuring the velocity quite accurately. And he gets these data points, so he sees, draw a line through those, and that's the expansion rate of the universe. That's that line that connects the dots. And there are words here to describe this process. But the real value is down here. We now know this because we have the Hubble Space Telescope, and many other, even modern ground-based telescopes can do extraordinarily good measurements of the distance to distant galaxies by looking at redshift with incredible precision. So we're not blaming Hubble because he had limited ability to measure the distance. He could measure velocities, but the real value is down here. The thing to recognize is the expansion rate of the universe is connected to the age of the universe. A highly expanding a universe that has a very high expansion rate is a young universe. It has a limited lifetime. And we discover, again, consulting with geologists, there was a problem with Hubble's data. It implied that the universe, which was much younger than the age of the oldest known rocks, the geologists had found. So this looks like a good spot to take a break. I promise you, I will try to get my throat under control. It's almost exactly 2:00. So let's resume at 2:05, and we'll get into how we actually measure the distance to these distant objects. All right, it's 2:05, and let's take a look at people have written notes about getting access to the lectures. And I can't tell from Chris's note. It says the link to the lectures. Do you mean the lectures themselves or the videos of the lectures? Because then I see reference to signing into YouTube. You shouldn't have to sign into YouTube. It's public. Okay. I'll dig into this and later today I'll send help because I want you to be able to see the notes and the videos. That is a mystery. All right, well, let's not get derailed too much. So let's talk about what we now call the cosmic ladder. This is the structure that has been built through 100 years of effort to figure out how to measure the distance to distant objects. Here's a way to think about the cosmic ladder. Here we are on Earth, and if we want to know the distance to the planets in our solar system, we can use radar. We can send a signal out, which bounces off the planet or the moon or whatever, and we just measure the time until we get a response. That does not work when we're dealing with stars. For stars, nearby stars, we can use what's called parallax. So here's Earth in June, looking at this object. This is the sun. We look at this object and we will see behind the object in the very distant, high distances, we will see objects that don't change their position because they're so far away. So we could take a photograph of this object, notice the position of these distant objects, and wait 6 months. So that was June. So here we are in December. We take the same picture of the same object, and we'll see the apparent position of these distant objects will change. And by measuring that change, we measure the distance. There's a little arithmetic involved because we know the distance to the sun. That's called parallax. Then there's a scheme that involves trying to characterize the temperature of stars, what we're going to skip over. The really powerful technique is to look at the very interesting phenomena discovered by a woman astronomer in the earliest 20th century when there were very few women astronomers, these so-called Cepheid variables. These are stars that change brightness in proportion to the period of their brightening and dimming. There's a relationship that was found by Henrietta Leavitt that relates the brightness of a star, the inherent brightness you would measure if you were near that star, and the period of oscillation of brightness, not a period of motion, but of a brightening and dimming that occurs in these particular objects. They're rare, but they're out there, and they're in all the galaxies that we look at. So how do we exploit that? Well, this is a set of information that we can use if we can find a Cepheid variable near an explosion of a small star called a white dwarf. If you can find that relationship, then you know the power output of the exploding white dwarf star, because we know the distance to the Cepheid variable, because the nearby Cepheid variables give us what is called a standard candle. So a nearby Cepheid variable in our galaxy tells us that if its period is 3 days, then we know its inherent brightness. And if we see a 3-day Cepheid variable in a distant galaxy, we can conclude that it has the same brightness as the one near us that we can measure using parallax. So there's a series of steps that can be taken to get the distance to dim objects. And none of these objects are bright. Once you leave the Milky Way, you have to have very sensitive technology. These exploding white dwarf stars have to be of a particular type, called it type 1A. And the presumption that so far seems to be working is that all the type 1A supernova events have the same power output. And I'll show you the proof here in a second. Then here's an explanation. Sorry, here's an explanation of what produces that supernova event. It's when a white dwarf star, a collapsed star, has a partner that's dumping matter onto it. Eventually, the matter in the white dwarf exceeds a limit that we calculate from quantum mechanics, and the white dwarf explodes. So here's an animation of that process. Here we are. Here's the sun. Here's the orbit of Earth, for example. And here's a Cepheid variable somewhere out in the Milky Way. So this is all nearby. And if you look at all these blinking lights, that's to indicate that these are Cepheid variables blinking, where a dim one is blinking fast, and the big one's blinking slow. When I say big, I mean more, producing more light output. So we can see this Cepheid variable out here and infer its brightness because we have one. I have to repeat this now, because we can measure the distance to this Cepheid variable that's nearby, right there. And given that information of the variable stars, we could estimate the brightness of this star. Now, in the old days, when Henrietta Leavitt was doing her initial research, she could only see out into the galaxy with limited range because the sensitivity of telescopes at the time was not nearly as good as it is now. Now we can reach much farther out into the Milky Way and measure the distance to Cepheid variables. But there are places near us that have Cepheid variables, particularly the Magellanic Clouds that are near the Milky Way. They're in the gravitational grasp of the Milky Way, and we find Cepheid variables there. And every once in a while, someplace near us will produce one of these type 1A supernovae. They're very rare, but because we have the Cepheid variables, we know the distance to the supernova event. We'll get into this gradually more and more as we go through the rest of this hour. In addition, we can see these flashes that are appearing on the screen represent type 1, type 1A supernovae in distant galaxies, and we can see these because they're very bright very briefly. When we put this whole thing together, we get a scale of the distance to the galaxies that are of interest in measuring the expansion rate of the universe. So here's, if we could step away from the Milky Way, you would see the Milky Way here. And here are the small and large Magellanic Clouds. This one's only visible from the southern hemisphere. Here it is. And it has Cepheid variables in it. And this is a picture of Henrietta Leavitt. And here's what we get from using Cepheid variables in the Large Magellanic Cloud and in other places in the Milky Way. That is, this is the variability in days of the stars we're looking at. And here's the luminosity that they have. And so we can draw a line through these, and that's the reference line we use as we reach farther out into the universe. So here's, again, parallax. The parallax gives us the distance to nearby stars. The Cepheid variables calibrate where type 1 supernovae might be. And these circles are Cepheid variables in a galaxy called 9391. And right there, there's a supernova event and these last for a matter of weeks. So you have computers scouring through all the data that we're getting from the Hubble telescope and James Webb and so forth, looking for supernova events in galaxies where we already have measured the variability of Cepheid variables, and that gives us the distance to the supernova event. And all kinds of technical issues have to be overcome to make this work. Obviously, we're just skimming over the top of it. So the most distant type 1a supernova we've ever seen occurred 10.2 billion years ago. And we can see it if we look right here. Here's the host galaxy for this event. And then there was something happened that was detected by one of our telescopes. But because we know what the galaxy structure is in the vicinity of the transient event, we can digitally remove the influence of the host galaxy. And there's where the type 1a supernova event occurred. And it occurred, this is a Hubble photograph. It occurred right inside that box. So thousands of graduate students working thousands of hours per day are managed to write the software that finds these transient supernova events. Here's what one of them looks like if it's close enough, like 1987A. If it's close enough, we can study it in detail. You'll see the light output changes over time, over a period of 15 years. Because the debris from the exploding white dwarf star is expanding out at less than the speed of light and it gradually encountering the dust and gas that was around that planetary system, that stellar system before the explosion. So you see it was dim there and it's bright there. In the Milky Way, we know of a supernova in 1604 where all the stars in the sky when that event occurred were dimmed by comparison to the one bright object that appeared in the sky back in 1604. There's also the idea that the events described in the Bible relate to a supernova event that would have lit up the sky back in year 0. So we also, when this occurred, we also see just slightly after the light arrives, we see an output of neutrinos, elusive tiny, tiny particles that are produced in these kinds of explosions. And we could correlate the distance to this supernova event because we saw a burst in neutrinos and brightening in all of our telescopes. So here's another one here's an image that shows the 1987A in the radio spectrum, the visible spectrum, and in the X-ray spectrum. And just a week ago, we got a new picture from James Webb, I think, of the detail of the leftover star in the center of this explosion. So there's the Crab Nebula, which is the result of the supernova event right there. Okay, and this shows the detail of how the white dwarf and a companion interact to produce these explosions. Now, here's how we know what we're doing, because we know nuclear physics, and we know the radioactive rate of decay of isotopes of various elements, including nickel, cobalt, and 2 isotopes of cobalt. So we know that in the type 1a supernovae events, nickel gradually it fades away, and in the process, it produces cobalt. And these events produce light that we can see. And the cobalt fades away, the 56 cobalt fades away and leads to isotope 57 of cobalt. And I'm not going to read this to you, but this whole process takes, well, you'll see here, days. 6 days for the nickel to fade away to half of its original intensity, and 77 days for cobalt 56 and 272 for cobalt 57. And here's data from a pair of supernova events where we see this. This is the fingerprint that tells us we're looking at the type 1A supernova event that we want to correlate with a Cepheid variable star and get distance. And here's a group of 22 of these supernova events, and you see they're not all falling on the same line, but they're all pretty close. So there's a lot of art to figuring out how to interpret this data and make sense of the distance to the galaxy that produced the data. The other thing we find is what happened in the location of the event took, say, like a month. But we see it happen over a period of almost 3 months or 4 months because of relativistic effects. So we have a lot of insight into what's going on when we observe supernova events. In addition, we have lensing as a potential mechanism to measure distance to the more distant objects, ones so far away. These quasars are so old and so far away that we can't use the supernova process to get their distance, but lensing gives us insight into that. Here's the redshift. I'm not going to go into a lot of detail. I think I've shown you this before. What this shows is we have a parameter that is the measure of the shift in the wavelength of light from atoms that we recognize. In this case, hydrogen and oxygen produce these spikes. And as we look at different galaxies, we can assign a redshift number, namely Z as the abbreviation. And you see the same structure occurring in different galaxies that are receding from us at different rates. And here's what's interesting about the Z value. This just defines it's what we measure compared to what was emitted. And we know what was the wavelengths that were emitted because we have measured these things in the laboratory. You do a little arithmetic, you get this. But what's really interesting is if you take the Z value, let's say 0.087, and add the number 1 to it, that tells you how much bigger the universe is now than when the light was emitted. So the Z value of 0.087 would give us a 1.087. That means the universe was 8% bigger, is 8% or 9% bigger now than it was when the light was emitted from this particular galaxy. So in your mind, if you happen to see a Z value thrown around in a description of some galaxy like this one, just add a 1 to that, and you know that the universe is now 37% bigger than it was when this galaxy produced its light. I'm not going to describe this right now. I'm going to concentrate on some other things. Now, using all these techniques that have been in gradual development for the last 100 years, we have a measurement of the Hubble constant. That's what we use to measure the expansion rate of the universe. Here's Hubble's work. I've already pointed out that because of his limited telescope and measurement technology, he got the wrong value. Oh, and I'll point out again, you can have fun with this little clip about expanding universe. So here's what Hubble was getting, this kind of expansion rate. Here's what we get these days, a very different value. And with a little manipulation, you can use whatever the Hubble constant is, turn it upside down, get the reciprocal, and that's the age of the universe. And here's why people were troubled by Hubble's results in the 1920s and 30s. Because if you used his very high value for the expansion rate, that meant if you put a big number here, you get a small number for 1 over the Hubble constant. And it meant the age of the universe was too small. And I'm going to show you. Here's the Hubble constant back in the 1920s and 30s. These came from Hubble and people working in the same field. Over time, the Hubble constant, because of better and better measurements, the Hubble constant has come down, 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 and it's now right around that value of 70 that I mentioned to you before the break. So that's good. We think we're close to the right value. However, I use the word here, sadly, we have multiple ways to measure the Hubble constant, and they don't agree. And it's a troubling thing. It's called the Hubble tension. And astronomers are working around the clock to figure out why are we getting wrong numbers. Not the wrong numbers. We can't get numbers that agree. So again, here's Hubble's data, 1930s, gradually producing this range of values, modern range of values. The interesting thing is that if you use Hubble's original results and compare them to the age of the universe, you would find that the universe and Earth were the same age. And that might have been okay, but gradually as time has gone on, we see the truth that the improving measures of the expansion rate of the universe imply that the universe is about 14 billion years old, and Earth is somewhere around 2 to 5 billion years old. And in fact, these are the estimates that existed over time. In the 1920s, geologists thought that Earth was about 4 billion years old, which is pretty close to the actual value. And they stuck with that. They kept making better and better measurements using radioactive data and all that sort of stuff. And now the accepted value for the age of Earth is about 4.5 billion years. And that is smaller than the age of the universe. So that implies there was time for the Earth to form and evolve to the state we see today. So this conundrum that existed back in the early 20th century, where the age of Earth was bigger than the age of the universe, that problem has been solved. Now, what hasn't been solved is this issue of the Hubble tension. So here we're looking at modern data, roughly the last 20 years. And back in the early 21st century, a lot of ideas on how to measure the Hubble constant, and various measurements were made, and they all had large error bars. So the estimates were plus or minus 20%, which I've tried to indicate with these balloons. So a measurement made in 2015 using supernova data said that the Hubble constant was this value with a big error bar, and measurements made using the cosmic microwave background were far different. Here we have an estimate in the mid 70s for the Hubble constant. The cosmic microwave background was predicting values around 68. So there's a big difference, but nobody cared at the time because the error bars were so big. The assumption was the precision of our measurements was not that good. It wasn't until around 2015 that people had refined the measurement techniques of both measurement methods and could see there was a gap here, and that gap has not gone away. We now have a new scheme based on the behavior of old stars called the tip of the red giant branch, and the hope was that that was going to resolve which of these was correct, and it fell right in the middle. So this is a conundrum. People are still anxious about this. So here's another way to draw this, that in the early 2000s, the Cepheid variable technique using Cepheid variables, and supernova events gave us an average value of about 72 with big error bars. And the cosmic microwave background is the black dots. See right here that they agree. But gradually over time, we got to about 2013, 2015, you could see the two sets of data do not agree, and the tip of the red giant branch lies right in the middle. And this is mysterious. In fact, Wendy Friedman, no relation to me, was just interviewed last week about this problem by Neil deGrasse Tyson. We're still talking about this. She's one of the pioneers of trying to figure out what's going on here. And it matters because if the Cepheid variable method is right, that means the Hubble constant is bigger, much bigger by roughly 10% than the microwave background data. And that tells us we don't understand the age of the universe to better than about 10%. We have a new technique using delayed lensing, which I'll illustrate in a second. And it too falls between the two most mature methods for measuring the expansion rate. The Cepheid variable and the cosmic microwave background are the two most mature methods. So there's some notes on here you can read. Now, what is this red giant branch? So to talk about that, we have to look at this wonderful diagram, the Hertzsprung-Russell diagram, that tells us how to classify stars on what is called the main sequence. And our sun is a part of the main sequence. And this graph shows us the temperature of the star with the lowest temperatures here and the highest temperatures here. And it shows us the luminosity, the brightness of the star on this scale. So there's cold, old stars are very dim. That's what that shows us. And as you look at stars of higher and higher temperatures, you eventually come to our sun that has a relative brightness of 1. And then there are stars that are remember, the temperature goes higher as we go to the left. And then there's this branch. But the giant stars, which our sun will become, our sun is gradually going to get hotter and hotter and use up its fuel and become a red giant. That's what this illustrates. Now, what's unique about this is this. This is the same drawing, and the main sequence takes you to this split right here, the branch. And the branch, we go to the red giants. That gets us to here. And what's interesting is, as these red giants age, they eventually settle into having a constant luminosity at every temperature. And this is a scheme that can be used, that Wendy Friedman uses, to measure the distance to these objects. Because you can tell when you can pick out the stars that have gone through this process, and you know that their brightness does not change as they get warmer, as they age. And so she's done an extensive study of this, and it unfortunately does not resolve the Hubble tension. Now, delayed lensing is an interesting scheme. We've talked about these mirages that come from an individual, a distant object, distorted by an intervening galaxy or galaxies. And how do we know that these bright points here are all part of the same light from the same object, which is distorted by this intermediate galaxy or set of galaxies, a galaxy cluster? And the way we do that is we look at the spectra of each of these spots and compare their spectral lines. And there we thereby get the chemistry of the object that produced these 4 mirages. That tells us if they agree, they have the same chemistry, and they have the same redshift. All this light came from the same source. Now, what's unique about this is to understand why this light from these very, very ancient sources is so bright. What's going on? And the answer seems to be it's light from the disk of debris around a supermassive black hole, heated up to stupendous temperatures by that matter as it falls into the black hole. There's friction in that disk that rotates around the black hole, and that's what produces these bright objects that we, in some rare cases, can actually see. What's more, we can do, so here's the formation of those spots by an intervening galactic cluster. Now, what's really interesting is that the black hole in the center of this way distant galaxy, that the amount of matter being digested by that black hole is not constant. In fact, if you measure it over a period of time, if you measure the brightness of one of these spots, you'll see it varying like this orange curve varies as debris was falling into that distant black hole. If you look at a different one of the spots, this one here, you see the rate at which it's ingesting material. But if you look closely, you'll see that that blue curve can fit right on top of that orange curve. What we're seeing here is the same light taking different paths to come to us. And that's further confirmation that these four bright mirages all belong to the same black hole in this distant galaxy. So work is being done to develop a technique using delayed lensing to get the distance to this ancient galaxy. And it all comes from noticing that the time variation from different mirages is the same. Here's recent data on this. This is one of the reasons I call this this class modern cosmology, because if you buy a book on cosmology, you will not see this because these results are coming in on a weekly basis. So here's what the Hubble telescope measured in 2016, and you see here bright objects circled. And 2 years ago, James Webb Space Telescope, took a picture of the same spot on the sky, and there the same objects are located. And all these streaks, that streak is all from one galaxy distorted by intervening galaxies and galactic clusters. And if we dig even deeper and we take this streak here from James Webb and look closely, circled here are two sources of radiation. These are supernovae that occurred billions of years ago in the galaxy that produced this streak of light. But you couldn't see them here except in cases where they're had a dark background. What's more, we can go even deeper and take a look at this. This is from James Webb very recently. And there's a supernova event in that distant galaxy, and there's another one. And we see here one of the authors of a paper that describes this says, we're going to watch these supernova events, and in around 2035, we'll see the end of the activity circled here. So we know where to look now and look for the delayed lensing of a supernova event in the ancient world. Let me check and make sure there's so right now, I don't see anything in the chat room except the issue about getting to the lecture notes. we have some time. Let me stop and ask, do people have questions? You can unmute if you have a question. Or put something in the chat. Okay, if not, we're going to keep going. So what I'm telling you is that James Webb, which could be functioning, hopefully will be functioning in 2035, or will have been replaced by a more modern version of James Webb, should see more details about these supernova events, because the light, let's go back a little bit, the light coming to us from another path could take years of delay. When I showed this shows time delays on a scale of days or weeks. A year here is about the width of that beige area, but a long path would take decades to get to us and show us the same kind of result, and that's what this is depicting. But nonetheless, we're stuck with this Hubble constant problem. And so to put things in context, here's Hubble's data. Here's what we get from the supernova data calibrated with Cepheid variables. Here's what we get from the cosmic microwave background data. And these two curves do not agree. Now, one reason that they may not agree is the following. Supernova events are based on Cepheid variables and supernova explosions that are relatively close to us on the scale of the size of the universe. We're looking back 3 or 4 billion light years, I think, is the most distant supernova event that is bright enough to be processed. So we're looking at the expansion rate of the universe in our neighborhood. The cosmic microwave data comes from the earliest time in the universe. Remember, it appeared at 380,000 years after the Big Bang. So the cosmic microwave background data has traveled to us for the entirety of, almost the entirety of the life of our universe. But in order to interpret that data, we have to have a model of the expansion of the universe. So here we're making exact measurements of the nearby expansion rate, but we can't see the whole history of the universe. And here we're seeing the whole history of the universe, but we don't actually measure the expansion rate. We have to use a model for the expansion. So this is the gap that's under a lot of intense scrutiny now to try to resolve this issue of the Hubble tension. So now let's look at some calculations I did using the Friedmann equation. If the Friedmann equation is right, and it seems to be, this is how the size of the universe has grown since the Big Bang. Here's the Big Bang there. Based on what we know now about the energy density, the current energy density, and the current matter density of the universe, we would have a very rapid, right here, a very rapid expansion for a short time, then a period in which the expansion rate was relatively constant or slowing a bit because of the influence of gravity. And right around here, sort of 4 billion years ago, we see the expansion rate increase. And we right now are right there. And this is for you math types. To model this requires manipulating hyperbolic functions and using these parameters for the expansion rate, the age of the universe, and a 70% density of dark energy, 30% density of matter. This is the curve we get, and we are right there. So this is how the the size of the universe has expanded up until now, and this is how it's going to continue to grow. But because we have this Hubble tension of a low value from the microwave background and a high value from Cepheid variables, this is the rate of expansion, and it's not the same for these two possible values. So you see a very high expansion rate in the early universe before 1 billion years, slowing under the influence of gravity, but still expanding. And then a minimum expansion rate right here, and then growth that depends on which of these values is correct. And we don't know which is correct. And here, again, here we are right here at 14, roughly 14 billion years. So there's some detail here you can read. Now, the Hubble constant technically is the rate of expansion, which Friedman's equation gives us this, divided by the size of the universe. We don't know the size, but we can get this ratio, the rate of expansion and the relative size. And if we just do arithmetic, we get this. This is using Friedman's equation. And what we now know, this is how the expansion rate of the universe will change over time. We are right there. We're at just under 14 billion years since the Big Bang. So the early universe had a very high expansion rate, slowing down, and eventually, because dark energy will be the overwhelming factor in the universe, because it's constantly being produced and filling all the voids in the universe, gradually the expansion rate will settle down to a single number, just under 60, and it'll sit there as the universe expands and expands forever. And during that time, this expansion rate will carry the galaxies away from each other. And far in the future, say 100 billion years from now, astronomers in the galaxy that is formed by the Milky Way and Andromeda, which are going to collide, those future astronomers will not see any other galaxies. Those other galaxies will be over the horizon I illustrated that you have to deal with if you're on a ship and you look out to the horizon. There's a limit to how far you can see. And if a distant galaxy that maybe doesn't even exist now sent a signal toward us, no matter how long we wait, we will never get that signal. And this is the rate, this number's right around just under 60, will replace the value that we currently measure somewhere in between 65 and 75. That's what Friedman's equation says. We don't have to do that. You can look at this if you want. This is the expansion rate, a Hubble constant, as a function of z, the redshift. And at high redshifts, the expansion rate becomes a constant. All right, now let's look at something that's always confused even in the non-scientific press. They get this wrong all the time. Here's z, that's the redshift value. And here's what is called the look-back distance. That is, how far away is an object that has a particular redshift, let's say 4. That means the lines of hydrogen that we measure in the laboratory are seen in that distant galaxy at 4 times the wavelengths that we measure in the laboratory. That object is now nearly 25 billion light years away from us. So let me show you some examples of how this gets confused. Here I've included on here redshift of 8. So if we look at a galaxy at a redshift of 8, it produced the light we see starting around 650 million years after the Big Bang. And if it still exists, since 13 billion years have gone by, it's now nearly 30 billion light years away from us. If we keep looking back for the oldest light, we find the Z value of the cosmic microwave background is 1100. So it was produced at 380,000 years after the Big Bang, but its wavelengths have been shifted by a factor of 1100. And if we do this arithmetic, which comes from the Friedmann equation, we find that that distance is 45 billion light years. That's why I have used that number over and over again. The distance to the cosmic microwave background is 45 billion light years. So if we look in one direction, we see the Big Bang leftover radiation, the microwave background, 45 billion light years away from us. And if we look in the other direction, the distance between the most distant objects in the universe, sorry, I gotta make a change here. There's a typo at a critical point. No, let me think for a second. Yep, it's okay. The distance between the most distant objects in the universe is about 90 billion light years, 45 billion in each direction from us. And all observers in the universe would see that same thing. They all see this value for the redshift of the microwave background. And it's been estimated that objects even farther away, like over 60 billion light years away from us now, is part of our universe, but it's not part of our visible universe. It's not part of the universe that will ever get its light to us because of the rapidly increasing expansion rate of the universe. So here's in this inset, we see the calculation that applies right here. Here's the redshift going out to 1100. And if we look on this scale, we see that's almost 45 billion light years distant from us. Now, here's where people go wrong, particularly science reporters. They always assume that when the scientist reports a redshift of a particular number, that you multiply that times the speed of light to get the distance. And that's not true. For example, the age of our universe is right around 13.8 billion light years. That happened long ago. That's a Z of 1. Here's a Z of 1, and 1.4 is here. The universe has been much bigger than 13.8 billion years for a long time. And I'll show you an example where, oh yeah, for your math types, you do the calculation. So here is Scientific American from a recent edition, 2022, where a reporter looked at a science article which reported that a galaxy had been found at a distant with a Z value of 13 or something. And they said, well, that means it's 13.5 billion years away from Earth. That is not true. a Z of 13.5, if we look it up on the actual curve, is 33 billion light years away. And this is a reputable journal with editors and all that sort of thing. So Stephanie, who wrote the article, I wrote to her and I said, no, you have talk to an astronomer before you pick these numbers because you did that wrong. But it's hopeless because of virtually all the articles that use the redshift value get the distance wrong. Here's another one. The redshift of a particular galaxy that produces radio emissions, the redshift was 1, and they said, okay, that's 8 billion light years away. No, it's not. It's 11. I mean, we should try to get this right. Now, we also have look back time, and this is where we look at the highest values of redshift, namely 1100, and we see that it points to an age for the universe of 13.8 billion years. So a redshift of 3 comes from 11 billion years. A redshift of 1100, which is off this chart, gives us the age that everybody, all the professionals use, that our universe is 13.8 billion years since the Big Bang. And here's, this points to a question that was asked right after the first lecture. What is the speed of the most distant objects? And this blue curve is the way you calculate that. And you see that at the very highest redshifts, like redshift of the microwave background, that's receding from us at about 3.3 times the speed of light. But there's anywhere beyond this point, a Z of about 1.5, the objects are receding at faster than the speed of light, and that's fine. The objects are not moving through their environment at that speed. The space between the galaxies, the Milky Way and that distant galaxy, that space is expanding at faster than the speed of light. And so this blue curve is the right way to calculate the recession velocity from the redshift. So here's a drawing that was done before the Hubble James Webb was launched. So here we are in the present day, and this tells us the Z values that existed when Hubble was the only observing platform. And you see they were reaching back to 8 to 12. The Z values were 8 to 12. So they were getting light from objects in this range between 13 and 13.4 billion years ago. Now, James Webb has seen objects here, and they break this record every week. And I've shown you this before, but now let me reiterate. This is a measure of the Hubble constant for a nearby galaxy and a whole bunch of other galaxies that are out there, done by different methods. Acoustic oscillations, looking at quasi-stellar objects, which are those giant black holes. And you get these data points with error bars, and the error bars get bigger as you go out farther. And if you pick the right numbers, if you include in the Friedman equation, if you include 30% matter and 70% dark energy, you get this green line, which matches the data. The other choices you have for the relative amount of dark energy and matter in the universe do not match the data, but this 30%, 70% does. So we're confident about this, but we have this nagging problem about the Hubble tension. Here are some numbers you can refer to. The ones in orange are sources of controversy. Here's the Hubble constant, but we have an uncertainty there of about 10%. No one is happy about that. Dark matter we've measured, but what is it? That's why I highlighted this one in orange. And dark energy, we've measured it. What is it? We don't know. So here's the way the universe was configured today. Mostly dark energy with some dark matter and just a few percent atoms. Here's the way it was in the very early universe. Dark matter was there, and it's been diluted by the expansion of the universe. There was an influence from photons. They've all been diluted. Neutrinos have been diluted. And the atomic matter was much bigger, but there was no dark energy at the time. The universe was so small that dark energy did not play a role. It was the width of this line, but now it's dominant. So with that, we're going to end for today. And I am going to work on the problem of why you can't get to the lecture notes. And as I said earlier, you should be able to jump into YouTube with no problem. There's no restriction. You don't need a password to get to my YouTube stuff. So I'm going to work on that. And I'll work with the OLLI people at CSU to get you some links that we know are successful. Okay, with that, we're going to stop. Let's see, chat. We have what? Oh, thank you for the nice words. And we're going to end the session. And I'll see you next time.